We're going to do a tiny sidetrack here. We saw an example last time where the degree of the numerator was bigger than the degree of the denominator, but we kind of got off the hook with that because the denominator actually canceled out completely. So what we want to tackle next is what happens if that doesn't just cancel out. We've said that we'll get a horizontal asymptote if the degree of the bottom is bigger or if the degree of the top and the bottom are the same. So this is going to be the other possible scenario. And what I need to work on first is just a quick algebra trick that's going to help us figure out what is going on. So this is technically an improper fraction. If you remember back to, like, I don't know, grade school fractions, we can have 1/2 and 1/3 and 2/3, but as soon as you get 4/3 where the numerator is bigger than the denominator, we would call that improper. And with rational functions, an improper fraction has a higher degree on the top. And the trick will be to rewrite it as more like a mixed number. So if we think about the way 4/3 could be written as 1 and 1/3, I generally will never do this with numbers. I don't really want to work with 1 and 1/3. I'd much rather work with 4/3, but sometimes it's nice to see that that's what we're really talking about. And that's what's going to be helpful here. So the way we do this is with long division, polynomial long division, which exactly follows the algorithm of regular long division. So I'm going to do a really quick reminder of what regular long division looks like, because I don't know about you, but if I don't go and think about it, it's not fresh for me. It's not something I use all the time. So just for example, this would be if we were starting with the fraction 242 over 7. We would set it up 242 divided by 7. And we would start from the hundreds place here and say, okay, we're going to see how many times does 7 go into just the 2. And the answer is it doesn't. It's too small. So then we'll include the tens placed in as well. And we'll say, how many times does 7 go into 24? And the answer is the closest we can get is 3. So we then say, okay, well, 7 times 3, that's 21. So how much did we leave behind? So we'll need to subtract that 21 off, and we'll say 24 minus 21 is 3. And then we need to bring down the 2 that we haven't dealt with yet. And we ask ourselves the question again at this point. We say, how many times does 7 go into 32? And the answer here will be 4. So we then say, okay, 7 times 4 was 28. So how much do we have left over now? And 32 minus 28 is 4. So this is our remainder. And then the important part for what we're about to do is to realize what your answer really means. It means that 7 went into 242 34 times with a remainder of 4, which hasn't been divided by 7 yet. So with it's really 34 and 4/7 times. We can turn that remainder into a fraction, and that's going to be crucial for the polynomial version of this. Okay, so let's check it out with polynomials. There's a couple of really picky things. Anytime you have an algorithm like this, you're going to have to be really, really careful that you set everything up right. So we want to divide x minus 3 into the top polynomial. And here's where the picky things happen. You need to line everything up perfectly. So you have to write your polynomial in descending order. You have to put the biggest power first. And then you have to make sure you represent all powers, or things can just get a little confusing. So even though there's not an x squared in that numerator, I'm going to put a placeholder in there. I'm going to say is 0x squared. So just like in the base 10 system, how you have to put a 0 in for your tens, even if there aren't any tens, so 202. You need that 0 in there to get the right meaning. We'll do that with polynomials as well. And then the x's are next and the constants are last. So you always have to write both the divisor and, I don't even remember my terms, the numerator and the denominator. You have to write both of those in descending order and not skip any terms, or it's going to get weird. From here, what we want to focus on is really just the leading term in both. So how many times does x go into 2x cubed? Or probably the easier way to say this is, what do I have to multiply x by to get 2x cubed? You always need to make the first two terms match up. So I'm going to need to multiply by a 2x squared. And when I multiply that by the x minus 3, I want to make sure I distribute. So I'm going to get 2x cubed. If these first two don't match, you've done it wrong. And then minus 6x squared. And then I need to figure out what is left over. And those parentheses are really important because you are subtracting. So 2x cubed minus 2x cubed is 0. That should always happen. But you need to be careful with the second step here. We're going to have 0x squared plus 6x squared. So there's two negatives there that will cancel. And then you bring down the next term. You always need to have, if you started with dividing by 2 terms, you always need to have 2 terms to work with. If you started by dividing by something with 3 terms, you'd need 3 terms to work with. So we're not going to get too messy with this, but we are going to use it just a little bit as a tool. Next, I need to figure out how many times does my x go into a 6x squared. So I need to multiply x by a positive 6x to make those two match up. And again, when you do that, the 6x needs to get multiplied by both parts. So we will get the 6x squared. That should always line up. But then we'll also get a minus 18x. So don't fail to distribute or it'll mess you up. And then don't fail to distribute that negative as well. So 6x squared minus 6x squared leaves us no x squareds. That should always happen. You should always eliminate that first term. But then we have to be very careful. It's negative 11x plus 18x. So we're actually getting 7x here. And then again, we need to always have 2 terms to work with. So we're going to drop down a 7. And this should be our last step. We've dropped everything down. So how many times does x go into 7x? That's 7 times. We have to multiply by 7 to make them match. So this will be a 7x. And then we also need to multiply the negative 3 by 7. So it's minus 21. But then we subtract. So there's going to be that double negative again. The 7x's go away. We get 7 plus 21 is 28. So that's the process, and I'm just going to work through one, but I will put a bunch of extra videos, some extra videos in your extra resources for 7.3. So if you need more examples, it'll be there. I find that there's usually quite a few people who've done this already, but absolutely don't panic if you haven't, and it just takes you a couple of extra videos. They'll be there. I'm just not going to force everyone to go through them. So let me know if you're having trouble or go check the extra resources page. Okay, last thing here, I'm not quite done. What's going to be really important for our purposes is that we can then take this and say what it's actually telling us. So I'm actually going to go back to the original fraction. What I really learned here is that that original fraction is equal to a quadratic with a remainder of 28 that would need to be divided by the x minus 3 still. So by rewriting this as the equivalent of a mixed number, we'll get this polynomial that basically tells us how our fraction will behave when x gets really, really big. And the reason that we can say it's just the polynomial is because when x is really big, a proper fraction like this, where the degree of the bottom is bigger, will go to 0. So that becomes less and less meaningful as x's get bigger and bigger and bigger.